Right. Thank you very much. Thanks for having me here. I'm going to talk today about some work I did with David Hughes and our joint grad student Alex Jacobi. This talk is about singular limits, and it lets me open with one of my favorite Michael Barry quotes, which is, you bite into an apple, you see half a worm, that's pretty bad. You see a quarter of a worm, that's even worse, and so on. But like the limit of not seeing a worm at all is a singular limit. It's not so bad to not see a worm if you bite into an apple. So I'm going to talk about maybe a slightly less unappetizing limit today, which is that of taking an open system and making it increasingly less open. So I'm going to take the limit of a closed system as an open system that's not very open. And you can think about this for a few seconds and realize something interesting that happens in this limit. And so if you think about the behavior of something like a local spectral function, which is the Fourier transform of a local correlation function, in a discrete system with a finite number of levels, if the system is closed, the spectrum is just a bunch of delta function spikes. So it occupies, it occupies a measure zero set of the frequencies it could occupy. And it does that for any system size. If you take the naive system size to infinity limit, you'll say, oh yeah, the spectrum is always just a bunch of delta functions. But we know that's not how you should take the limit. The way you should take the limit is you broaden all these lines by a tiny amount, and then you take the thermodynamic limit with the lines broadened, then you take the broadening to zero. And that gives you a continuum spectrum, the type we used to in quantum matter physics. And one thing that's kind of interesting about this continuum, about this zero dissipation limit, is that nothing really happens to the spectral function, when you go from a weakly dissipative system to a totally non-dissipative isolated system, right? The spectrum, as long as the system is chaotic, the spectrum just goes smoothly to its zero dissipation limit. So you might say, well, is that an intrinsic property of the dynamics in the zero dissipation limit? And so a little bit of further thought tells you, well, it's not. It seems like a property that's distinctive to local spectral functions. If you consider something more general, like an out-of-time ordered correlator, which tells you, how big are operators getting? So operators get very big indeed in the zero dissipation limit, and the dissipation cuts them off. So something singular happens to most things you might consider in most quantities you might consider in the zero dissipation limit, and local spectral functions are, you might think kind of distinctive of the fact they have a smooth behavior in this limit. Nothing singular happens to them, but okay, so where does this divergence go? And so are these divergences intrinsic properties of the dynamics of a weakly dissipative system? And to address this question today, I'm going to take the Markov approximation. I'm going to talk about discrete time Markovian evolution. I'm going to take the weak dissipation limit of that. So if you haven't seen this, an open system is just universe, and you chop the universe up into degrees of freedom that you care about and degrees of freedom you don't care about. And so that corresponds to these are the system, that's the bath. The Markov approximation consists of saying that at each time step you bring in a totally new bath. So there's no memory in the bath. At each time step, the system is interacting with a totally new degree of freedom from the environment. So you can represent it diagrammatically like this. You have this one repeating unit, which is a system, new qubit comes into the environment, interacts with the system, goes away, right? And so you just do that over and over again to get the dynamics of a quantum channel. What you normally say is that you don't get to observe the environment, you only get to observe the system, and so you trace out the environment. That gives you this super operator that takes a ket and a bra from the system, that's to say a density matrix, and evolves it to another density matrix. So that's the object we're going to talk about, and the question I'm going to ask today is, what does the spectrum of this thing do in the weak dissipation limit? And so the key point is this encodes pretty much everything you could consider, right? It encodes the OTAC, it encodes like correlation functions, it encodes entanglement. So you might think that if correlation functions really so special, then there should be some kind of singular or interesting thing that happens in the limit of the quantum channel as you take the dissipation to 0. Right, and so fine. So, and that's what we're going to talk about today. I'm going to tell you that in fact there's something kind of surprising that happens in this weak dissipation limit, which is as you take so the quantum channel has a spectral gap, and the spectral gap stays open in the weak dissipation limit. So just to unpack that a little bit, yeah, for some reason I went to continuous time here. Yeah, I guess, so instead of thinking about a discrete time process, I can just think about a time periodic process. So that's to say a Lindblad form master equation with a time periodic Hamiltonian. And in principle, I guess also time periodic jump operators. And so what does the spectrum of this thing look like? It's in the limit where there is no dissipation, the spectrum lies entirely on the unit circle in the complex plane. That's just unitarity of the matrix. When you turn on dissipation, the fact that that trace is preserved means that you still have at least one eigenvalue precisely at 1. But the rest of the spectrum can do whatever it likes inside the complex plane. And so, for example, this is a typical behavior that it has, where all the other eigenvalues sort of wander into the complex plane. And so this distance, this is what I'm going to call the gap, right? It's the distance. It's sort of the distance from the special eigenvalue at 1. Yeah. Sorry? Okay. Right. And so what got me interested in this was this paper by Takashi Mori late last year, where he studied this question numerically for a generic chaotic Hamiltonian coupled in some generic local way to a bath. And what he found was that the gap of this thing stays open and remains order 1 as you take the limit of 0 dissipation. And this is rather surprising because, you know, how do you get from where there is strictly 0 dissipation, you're sort of on the circle, and you might think the spectrum has to evolve smoothly as you go away from that limit. And the point is, yes, it does in a finite system, but the thermodynamic limit and the 0 dissipation limit don't commute, and this leads to interesting phenomena. Okay, so something very similar was talked about a very long time ago in classical physics. I'm going to tell you about the sort of heuristic. Well, I don't know if it's heuristic. It's like some kind of picture of what happens to the spectrum. And so that's this idea due to David Ruel from a long time ago. And so the idea is something like this. You think about, so, you know, let's go back to my previous slide. You have the spectrum that's a bunch of points on the unit circle for a strictly unitary operator. As you take the system size to infinity, well, these poles all merge into a branch cut. So an eigenvalue is a pole of the resolvent of a matrix, which is, you know, the Green's function, if you like. And so in a finite system, you have a bunch of these poles of the resolvent matrix. Do you have a question?
Yeah, just a clarification. Yeah. So there have been some works by Andy and Frozen and others where they have shown that even a flow rate-driven system, very strong, right?
Yeah.
And a very weak dissipation is enough to thermalize it.
Yeah.
Is that related? What you are saying in some sense that
it's not unrelated. But the somewhat surprising thing is that, you know, thermalization. Yes, in some sense, the fact that the gap stays open is related to thermalization, but it's a different phenomenon, right? Thermalization is a property of local correlation functions. The gap is a property of everything. It's a property of the generator of dynamics. So the fact that the local correlation functions have a smooth 0 dissipation limit does not imply that that the spectrum of the generator does, right? The spectrum of the generator also generates the OTOC, for example, which doesn't have such a smooth 0 dissipation limit. All right, so that's the result. So yeah, I was talking about the resolvents of the matrix, and so it has a bunch of poles, and in the limit, in the thermodynamic limit, the poles merge into a branch cut, and so you have this sort of wall on the unit circle, and if you come in from outside, you know, you hit this wall. it's a branch cut, so you go through the branch cut, you appear, you re-emerge in a different Riemann sheet. And the amusing thing is that on the second Riemann sheet, you find, even in the isolated system, a bunch of poles inside the unit circle. And so these poles were seen, in certain, like, careful analyses of classical Frobenius-Perron operators, like, a long time ago, and they're called Ravel resonances. And we'll see, so the physics of these is what I'm going to talk about in the rest of this talk. I feel like I had a question back there. Yeah.
Size limit is finite gap. What determines its scale?
I'll come to that. But it's just it's basically like the previous question asked. It's really got to do with like the decay of local correlation functions. Surprisingly, so local correlation functions decay exponentially, and there's a time scale for that, and that turns out to actually set the gap of the Liouvelian. Yeah, so I mean, I don't really have a lot to say about it because I don't really understand classical physics. But the idea is roughly that you can think about the Frobenius-Perron operator in classical mechanics as the thing that evolves probability distributions under Liouville preserving, under measure preserving classical dynamics, right? And so the Frobenius-Perron operator is in fact unitary. It has a spectrum on the unit circle, and it turns out that that these statements that I'm making were made by Ruel for that object. Yeah, exactly. Yeah, precisely. Okay, so where does this phenomenon come from in terms that we can understand, in a modern sort of many-body physics way? So remember that if you think about the generator of open system dynamics, that's the Liouvelian or the quantum channel, you have a choice about whether to think about it in the Schrödinger picture or the Heisenberg picture. We normally think about the Liouvelian as evolving a density matrix, another density matrix. You can also, and that's sort of the right action of the superoperator. You can also think about it as evolving operators, evolving observables in the opposite direction, right? That's the equivalent of the Heisenberg picture. In the Heisenberg picture, the Liouvelian is not trace preserving because it's got no particular reason to be, but it has this important thing called the unital property, which is that if you act the Liouvelian on the identity matrix, it remains the identity matrix. If you don't perturb a system, it doesn't matter when you don't perturb a system, basically. And so this is, you can see this diagrammatically immediately. It's the fact that this U cancels out against the U dagger. Yeah. So question? Okay. So the argument that Maury made can be understood roughly like this. So if you think about the, if you take a matrix, you want to understand its eigenvalues, but its eigenvalues are the same acting to the left or the right, right? But the eigenvectors are very different, and the left eigenvectors have a simpler form to think about because of the unital property of Heisenberg evolution. So you can ask, well, what kinds of, so we're thinking about operators evolving in an open system, how observables evolve. And so the idea is as follows. So small operators, as we know, grow under Heisenberg evolution. They begin to occupy more and more space, right? On the other hand, the dissipation acts more strongly on an operator that occupies more space because an operator living in L sites has sort of L opportunities to couple to the environment. And so the basic idea, the intuitive argument is that any operator keeps growing until it gets very big, and then it dissipates, and then it sort of couples primarily to the bath. And so if you make a sort of rough estimate of this, you find that that the operator size gets to basically 1 over gamma, where gamma is dissipation rate, and at that point, the sort of operator growth and the dissipation are in balance, and you end up with an eigen operator. And so that was the heuristic picture that Maury gave of what causes the gap to behave the way he saw it to numerically. And so I'm going to, the rest of this talk is going to be a slightly more sort of detailed discussion of how this happens and how it's consistent with the fact that that even though the gap stays open, many objects have singular timescales like the OTOC does in the weak dissipation limit. How the existence of the finite gap is consistent with the diverging timescale in the dynamics. Okay, and so let's go back to what operators do in a system with no dissipation. And the basic idea is that an operator undergoes a biased random walk. So it's got any given time you commute it with a Hamiltonian, it has some chance of getting smaller and some chance of getting larger. The rate at which it grows larger is higher, the more ways to get larger than it gets smaller. And so an operator tends to grow over time. It grows via this biased random walk in the space of size. What do I mean by size of an operator? I mean, an operator is local, so it's the identity outside of a certain region, to the left and right of a certain region, and what I call the size of the operator is the distance from its right endpoint to its left endpoint. Okay? So it's like the leftmost and rightmost sites in which it's not the identity. Right, and so what dissipation does to this is you have this biased random walk, but then the larger operators also have some rate of just dying because they couple into the back and get traced out. So so now you have this this equation which gives you both the operator growth and dissipation, and what we want to do now is we want to analyze the spectrum of this not quite Markov process because dissipation kills norm. Okay. So there's a non-emission operator. What are its properties? Yeah. What? If there's even one conservation law, this picture gets significantly modified because, say, in the zero dissipation limit, the Hamiltonian, for example, is conserved. Right, and so you can check that the operators that correspond to conserved quantities don't undergo operator growth. So the energy, for example, time evolves to itself, right? The Hamiltonian time evolves to itself, and so that means that this argument does not work for such objects, for any conserved operator. Any conserved local operator doesn't undergo operator growth, and so the story changes completely.
Also, this argument is presumably implicitly in a finite number of dimensions, right?
Yeah, though I think as you crank up dimensionality, the effect becomes stronger.
But I mean, if you made it hyperbolic, then maybe it doesn't order one anymore because.
I think it still ends up being order one because the thing is it's a saddle point of these two processes, right? So the operator grows bigger and bigger until the change of the character of the operator is equally determined by the dissipation and the growth. So the balance between the dissipation and the growth is kind of fundamentally the same in any dimensionality.
Just a question. So X is indexing the step in your Markov process?
Yeah. So sorry. So X is So this is X is my x-axis. So it's the size of the operator. The time coordinate is t. Jamir?
Yeah, sorry, I lost the first minute, so let me see. Why is it biased? Why do you have an unbalanced gamma?
Because if you like, imagine doing Baker-Campbell-Hausdorff. There are more ways for an operator to grow big than there are for an operator to shrink. That's the bias. Okay? Yeah. Fine. So you write down. Yeah. Go ahead. No, that's not really clear, I would say. And in fact, they are functions of x at small x. I do not expect them to be functions of x once the operator gets fairly big, because then the operator is kind of spread out over a very large sample of things it could be. And at that point, it's self-averaging because it's it's a superposition of things that live in 20 sites. So it pretty much captures every operator that you could write down that scale. So I expect it to have some fine structure at small sizes, but the sort of large size part of the operator, which is what's relevant for the weak dissipation limit, is going to be pretty universal. It's like set by some intrinsic properties of the system. Okay, so so what you can do is, there's this non-Hermitian operator, and you want to diagonalize it. Yeah, and so it turns out that if you stare at it for a bit, you'll realize that there's a similarity transformation you can make going into a coordinate system where this operator is actually Hermitian, and so this Hermitian operator actually is just the Schrödinger equation in a linear confining potential. Okay, and so that's sort of nice because now you can take a continuum limit. You can think about this. You use standard WKB analysis to compute the spectrum of the sky, and what you basically find is that the similarity transform introduces an overall shift to the spectrum by an amount delta, which is basically set by the bias of this random walk. Okay, so delta I've written down here. It's like it's related to the difference between the left and right hopping rates. So it's the rate of operator growth. And yes, you can compute the eigenvalues and eigenvectors of this process, and they're the eigenvectors of this they're area functions. Okay, fine. And so one thing to get back to what Ash asked, at small operator size, there's sort of fine structure. So in principle, there could be a bump or a dimple around x equals 0. And in fact, in many of the models you can consider, there actually is this sort of little dimple. And if this dimple is strong enough, it can produce a bound state. And so the bound state's going to play. So whether there's a bound state or not, has a physical significance that I'll get back to in a minute. Okay, so the existence of bound state versus no bound state is not sharply defined when the dissipation rate is finite, but of course in the gamma to 0 limit, there is a sharp notion of whether this guy, whether the lowest eigenvector becomes arbitrarily big or is on order 1 size. So that becomes a sharp spectral transition in the character of the eigenvectors and also the eigenvalues. So they undergo some kind of singularity at that point. All right, and so you can compute the eigenmodes, and the key thing is now you've got to go back to the original frame. Remember, I moved into this weird frame, which is sort of roughly speaking a co-moving frame or something, in order to solve the problem, but now I need to go back into the lab frame. And in the lab frame, what you find is, the matrix is very strongly non-Hermitian, and its eigenvectors are all sort of pushed out and peaked at a value that's related to by the amount after shift by, which is related to to the overall operator growth rate. So the eigenvectors are very non-orthogonal, and in the limit of 0 dissipation, they sort of essentially all become sort of concentrated very close to this peak operator size. Okay. Yeah, and so I guess I said all of this, and so the key thing, the key to resolving why the existence of spectral gap is consistent with the existence of diverging timescales is that in this limit, the matrix becomes sort of arbitrarily non-Hermitian, becomes very, very non-Hermitian, and in a very strongly non-Hermitian problem, the gaps, the eigenvalues don't alone determine the dynamics. The eigenvectors matter. The way you can think about this is, if you have a bunch of imagine that you have a 2 by 2 matrix and its eigenvectors look like this. They're very close to parallel. You can write down, obviously these linearly independent vectors, you can write down anything as superposition of these guys, but you need increasingly large coefficients, right, in order to, and increasingly large coefficients and increasingly exact cancellations to express a vector like this in terms of a basis like that. And so what ends up happening is that as the eigenvectors become increasingly close to parallel, in order to express an initial operator, you need to involve gigantic coefficients that diverge, in fact, exponentially with system size. And so now you write down the time evolution, and you find that it has this feature where the coefficients goes 1 over gamma, And then there's also, the overall decay that's determined by a spectrum. But in order for these coefficients to get small, you need it to be the case that the time is big compared to 1 over gamma, right? So even though the spectrum has a gap, the non-orthogonality of the eigenvectors gives you this feature that you have diverging timescales. And so the gap. So okay, so far I've argued. Well, okay. So first of all, like, spectrum is gapped, but second, you should ignore the gap because it doesn't mean anything. So I mean, okay. So what am I? What's the message here, right? What is it? What is it actually? What I'm actually talking about? The point is correlation functions are a bit special because a correlation function corresponds to an operator that was small at the initial time, maybe got big, but then became small again at the final time. And so what that means is that if okay, so I don't know that. So this is the transformation, right? The transformation really distorts it distorts space in a way that's sort of trivial at the origin and becomes increasingly violent as you go farther out. But the operators that govern the correlation function never really get that big in the first place. Because if they did, they would never become small again. They wouldn't contribute to correlation functions. And so correlation functions actually do see the gap because the similarity transform is trivial near the origin. So that's mathematically the phenomenon that correlation functions behave nicely in the weak dissipation limit. That's where it comes from. I should say that the question about whether there's a bound state or not was initially considered in the isolated system by Saga, who is in the audience, I think. The transition, specular transition, talking about is related to that transition in the structure of correlation functions. Okay, so what actually relates? Why is the gap where it is, and what sets the physics of this time scale? So the idea is this. So you're trying to understand the following balance, right? So small operators try to grow; they try to get bigger and bigger. Big operators decay into the bath. And so the optimal operator size, this sort of self-similar operator size, is set by balancing these two rates, and that basically means that if this guy's bottlenecked by when it grows slightly bigger, the operator size of the saddle point is basically set by when the dissipation precisely matches, when the dissipation operator size L precisely matches the rate at which operator is being emitted from the origin. So that's what sets the size of the eigenmode, and so just to sort of wrap up this discussion, what you find is that there's sort of many different time scales, many different length scales for operators in the small dissipation limit. The eigenmode is of size 1 over gamma. Like Maury's original argument predicted, and like we sort of derived explicitly. You can ask, well, how big? Suppose I take a local operator and I just look at its size over time. How big does it get before it decays into the bath? What's the size of the OTOC? Well, that's actually 1 over square root of gamma. So it's not set by. It's much smaller than the eigenmode. An operator never actually gets out there. It never actually becomes similar to like the leading eigenmode of the quantum channel. It dies before that. And correlation functions are set by operators that don't even get that big. They sort of wander about at small sizes and then eventually refocus to be size 1 to contribute to the correlation function. Right, and so that's sort of that's the way these scales line up. Right, so this is all a sort of general picture in terms of things we understand about operator growth. Can I connect it to an explicit microscopic calculation? To do that, I need to think about ensembles of random circuits. And of course, for a random quantum circuit, there isn't, strictly speaking, an eigenvalue spectrum at all because they're not periodic in time. we can think about, instead of an eigenvalue spectrum, a spectrum of Lyapunov exponents of this process. And so that problem of computing the Lyapunov exponents can be explicitly solved using the technology of random unitary matrices, and that gives you that gives you, if you like, a strict lower bound on the Lyapunov spectrum gap, which then you can say is a lower it's a lower bound on the gap of a typical instance of a random circuit. So operators, so this entire story can be made explicit for that case. And so if you go through this argument, you realize something sort of amusing, which is that that the phenomenon of the weak dissipation limit being singular is related to spontaneous symmetry breaking in a slightly abstract problem, which is that so I guess this is not a random unitary circuits conference. I'm not going to introduce the StatMech model, but it turns out that the circuit average dynamics can be related to a particular type of Ising model, and so if you take an Ising model in an infinitesimal magnetic field, it magnetizes along the field. And then when you take the limit of when you take the zero field limit, you don't see that the state in the zero field limit is going to be the cat state. It just looks like, it looks like just the all up state or whatever. And the gap, if you like, is in this problem, the gap that I told you about is related to the spectral gap in the weak field limit of the magnetized Ising model, which is actually a cost of putting in two domain walls, right? And that cost remains order 1 in the limit as you take the magnetization to 0. What happens is that a totally different state from extensively far away suddenly shows up and joins you at the bottom of the spectrum. So, and you don't see that if you're working at any finite magnetic field. So yeah, so it turns out that the phase transition is also related to things that that people have discussed in random circuit sampling problems. The complexity of sampling becomes easy for like infinitesimal dissipation. But I can talk about that more if you have questions offline. Yes, I'm pretty much done. So the main thing I wanted to say is that that the spectra of generic local quantum channels, that's to say time-dependent Liouvilleans, remain gapped in the weak dissipation limit. The gap is related to the physics of local correlation functions, and all the timescales that diverge in the weak dissipation limit come from essentially the increasingly non-orthogonal nature of the eigenvectors of these processes. Right, so the non-hermiticity is important, and it leads to these diverging timescales that have no spectral meaning. Okay, so we still don't really have a deep understanding of what happens to the story. To address the question Jamir asked some time ago, once you put in conservation laws, and we also don't really understand how to derive an explicit how to understand the true eigenstates, the true left eigenvectors of the quantum channel. What I did was I replaced, I sort of substituted for the actual problem, which is an exponentially big matrix, the sort of coarse-grained Markov process in the size space. But if I go back to the original problem, how do I understand how the eigenvectors are distributed? It seems as if there should be some correspondence between the two things, but it's still a bit unclear how that works out. So yeah, that's it. So thank you for listening.
Questions? Jimmy?
Maybe it's the same question, but in disguise. So in the analysis, the fact that you get for density operator growth, the linear potential, the Schrodinger equation with linear potential is crucial. Now, if I ask you the reverse problem, right? We can solve plenty of potential wells with Schrödinger, like harmonic, infinite well.
Yeah.
What you get back as operator dynamics. Maybe it's crazy, or maybe you define some new interesting circuits in
So you
this
can
way.
think about operator dynamics in higher dimensions, for example, right? And so the sort of, indeed, so the size, so if you like, the decay of an operator of size, of linear size L goes as L. So that's where the linear confinement comes from. So if instead of that is working in 2 dimensions, then I'd have a quadratic
Nice.
potential, something like that.
Fun. And did you explore consequences of this?
Well, I mean, so what happens, yes, so an interesting thing that happens in these higher dimensional problems is that it turns out that there's, and this is not my result, this is like already in this old paper by Adam Nahum and Saga. So in higher dimensions, you always have a bound state. It turns out because the confinement is so steep that you find this discrete spectrum at the bottom always. In 1 dimension, you either have a bound state or not have a bound state.
Okay. So it's more.
Yeah.
Boring.
Yeah.
It's more boring. That's okay.
Can you use the microphone?
Yeah, while you were deriving and setting up the problem, Sarang, you said that you need a time periodic Hamiltonian. But so my question is why, what are the constraints? Can we relax that constraint? And if we just have the Hamiltonian and Lindblad sectors not commute with each other, will that be enough to prevent the zero mode problem?
No, because see, what happens is in the weak dissipation limit, if you have a time-independent Hamiltonian, then you have this conserved operator, right? There's the Hamiltonian itself. And so Hamiltonian, if I think about the operator growth, the Hamiltonian itself, it's not growing at all. It just sits there. And so when you take the weak dissipation limit, the Hamiltonian sort of trivially decays at the rate gamma because the only thing that's happening to it is it's dying in place. And so that changes the story completely. The existence of these local operators that don't sort of undergo this growth process. So that's the key thing. Now you could ask, well, could I make it like not periodic, but like random in time? So that's the random circuit case I was talking about. So the issue there is just there's no spectrum, strictly speaking, right? So you have to talk about Lyapunov exponents instead of eigenvalues and eigenvectors. But yeah, in that case, so that case is sort of qualitatively the same. It's just like less sharply defined.
Regarding your question about the conservation loss, so there is alternative approach to these Rayleigh-Poly coresonances where you directly target the truncating propagator, and there you get this conservation law automatically inside. So they will just correspond to the resonances on the unit circle.
No, yeah, that's right. So, I mean, I think the thing that's sort of nice about doing the problem explicitly is you don't actually ever have to truncate, right? You get this, the truncation is the exponential confinement. So in some sense, you're doing it, it's sort of doing it for you automatically.
What is nice about the other approach, so not to, is that here you have to take two limits. One is thermodynamic limit L to infinity, and another one gamma to infinity dissipation.
Gamma to 0, but yeah.
Yeah, there is just one limit to take.
Sure.
But then perhaps another comment about the random biased random walk setting. This is a classic example of a strongly non-normal matrix where actually a spectrum is irrelevant. So one should look at the pseudo-spectrum whose gap is actually 0.
That's right, yep.
But for the reasons you explained, the initial states that you propagate here, right, are localized. So for those measured 0 states, actually spectrum does matter. So it's kind of a funny exception.
Yeah, I mean, so I didn't, you know, this is not the talk I was giving today, but so in this other work about defining stable phases of open quantum systems, we looked at the issue of when the spectrum matters and when it doesn't. I would say that, so there's a notion of when you're in the same phase. So so basically if you take the steady state, you perturb it in some local way, in many local problems of thermodynamic limit, those local perturbations are always in this, what you call this measure zero class of things that are controlled by the spectrum.
It's not perturbation, it's your correlation functions.
Yeah, so this talks about correlation functions. In correlation functions, what matters is that the final operator is small. Right.
If you look at correlation functions of local operators, then
Yeah.
If you would look at some generic non-local ones, then actually you should look at pseudo-spectrum where the gap is zero and they will not decay.
Yes, but again, like the key point is that there's also, so what we find is that if you take, for example, a steady state and you perturb the channel slightly, then the sort of rate at which the original steady state relaxes to the new steady state is typically governed by the spectrum. And that's because, if you like, they're off by a local operator, and local operators are special.
We can discuss afterwards.
Let me ask a question about anti-unitary symmetries. So now I could imagine, for instance, giving the Liouvillean time reversal symmetry, which is not quite a conservation law, but it is some structure, and I suppose I could make it either a weak symmetry or a strong symmetry.
I think you can, I think it doesn't, I think anti-unitary symmetries have to be strong in order to be meaningful. There's a paper by Nigel Cooper about this. Unitary symmetries can be either weak or strong, but like, there's no good notion of an anti-unitary weak symmetry.
Okay,
but yeah, so if you have strong symmetry and you have like Tramers pairs, then maybe you have to like think about like, you know, maybe there's the sort of there's two guys at zero, everything shows up, goes in pairs. But I think that, yes, I don't really know, I mean, maybe other people have more insight into this, like what the implications of anti-unitary symmetries are in general for operator growth. I think there are not really any, because they're not, you know, there's no operator, there's nothing in the spectrum that just sort of sits, there's no operator that just sort of sits there without growing. Right? I think.
All right, well, if there's
no
further questions, thanks for having me.